Moving on to Pauling's rule number 3. So remember the crystalline structure, right? Where typically we have a cation surrounded by anions, creating some sort of structure, and then those bond together to create an overall ordered internal structure in a crystal shape, right? That means that for each of these polyhedron shapes, they have to bond together, right? They have to share either faces fit flat together, or maybe they can just share an edge, right? Or maybe they can just share a vertex, right? So which one is the most stable, right? What's most stable for these elements? Well, we have to think about the charges within these structures. Remember that like charges repel each other, right? So if you have two cations too close together, two positively charged ions, they're going to repel each other. And remember that at the center of each one of these polyhedral shapes is a cation. So the closer these shapes get together, the more unstable they're going to be, the more they're going to push each other apart. So how do you think stability will be affected if these shapes share actual faces or maybe edges, right? If they share a face, will this increase or decrease stability? Okay. Hopefully you came up with decreased stability, right? If they share a face, they're really close to each other. So the cations inside those shapes are going to repel each other. However, if they only share a vertex, right? If they only share a corner, that's going to increase the distance between those like charged cations and increase the stability. So Pauling's rule number 3 says that sharing of edges and faces between coordination polyhedra is inherently unstable, right? Because like charges repel each other. Now, Pauling's rule number 4 is just an extension of number 3, right? And it says that cations of high valence charge and small coordination number tend to not share polyhedral elements with each other. Right? So this says that anytime you have a high valence charge, such as Si 4+, 4+ is a pretty high valence charge, and a small coordination number, for example, in quartz, the coordination number is 4, that's fairly small. They're probably not going to share a lot of polyhedral elements with each other. And the SiO2 polyhedra actually only share vertices, right? They're as far apart as they can get, while still being bonded to one another. Some other examples of that is perovskite, right, which has a chemical formula CaTiO2, calcium titanium dioxide. And if we think about each individual element bonding there, the titanium has a 4+ charge. That's pretty high. And a coordination number of 6. That's, low-ish. So they're going to share vertices, right? They're going to share corners. They're going to want to be pretty far away from each other. However, calcium 2+, that's not a high charge, right? It's not really repelling things away from it very strongly. And the coordination number is 12, right? That means that it can be stable if it shares faces, right? Because that repelling isn't as strong. So the calcium part can share faces, the titanium part can only share corners.